Here we go. Let's get another lecture going. And this time we're going to start the first part of a two-part lecture on functions. So this will be quite a bit more intense than graphing lines. We're gonna be looking at a lot of other functions. We're gonna look at function notation in this two-part lecture. We're gonna be talking about some more definitions and things like that. Let's go ahead and jump all right into it. So just a little review of what we've been doing with lines. We've just said, hey, if I have a line and for example, maybe I write it y equals 3x minus 2 here. So if I have a line like that, if we want to find the value of y, what we've done is we've taken whatever value that we have for x, we plug it in, and then we just simplify down. And you can see I've done some of that work here for this line y equals 3x minus 2. I've taken x equals 4, and I've just plugged that right in, and then I simplify down and I get 10. And so then this would give us the coordinate point 3 comma 10, and that's saying that we know that if we were to graph this line y equals 3x minus 2, this point would be on the graph. We can also say that this point here satisfies the equation when x is 3, y is equal to 10. Oh, excuse me, not 3, that should be a 4. When x is 4, y should be equal to 10. And yeah, so that's how we get our point here. So keeping this in mind, this sort of idea that x is like an input, and I'm going to go ahead and write that down. X is like an input to this line. Y is our output. I put something in, I put 4 in, and I get 10 out. So that this whole x, y is like an input output. And what because that sort of idea of input and output just makes so much sense, it's so clear that that's what's happening here, we actually have a slightly different notation that is used a lot more often. And so what I'll say here is that sometimes instead of using that letter y, like I do over here on the left, sometimes we actually write f of x. And you'll notice how I pronounced that right here. That is going to be pronounced f of x right there. And so what we're saying here is just instead of y, we're going to write this f of x. And this f of x is just a slightly different notation. It doesn't actually change anything. I'm not doing anything different than I did before. I'm still just doing the same exact work. I'm taking 3x minus 2, I'm plugging in 4 for x, and then I end up with 10 when I simplify. I'm doing the same thing over here on the right-hand side, but the difference is just the notation that I use on the left. And so this notation that we'll start off with is f of x equals 3x minus 2. We use that letter f a lot because of the word function, and we'll get into what the actual definition of a function is in a bit. But we use that letter f a lot. A lot of other common letters are G, H, A, B, C are other big letters. Q, R, S, those are big letters that are used, but for the most part, we'll just use F. You could use you could use any letter you wanted but so I've got this F right here, F of X, and that's just a different way of saying Y. And the reason that we do this is because with this notation here, it makes it very clear that, hey, my function that I'll call it F instead of calling it Y, I'm going to call this function F. It has an input that I'm letting you know is X. And so when I plug in 4, you can very easily use this notation. I have an f of x, that's my function. Really what I can do is I can kind of just scribble out this x and I can just put a 4 in there. And so what's inside of these parentheses right here, what's inside there is really just an input, right? And remember, we said x is an input, y is an output. So when I write it like this, I have x as my input, and that's very clear here. And you can see I got my function, 3x minus 2. And so x is my input, and my output is just 3x minus 2. It's whatever I get when I plug in a particular x. In this specific case, when I plug in 4, I get 10. Here, if I don't plug in anything and I just leave it with an x in there, then my output is 3x minus 2. And so this is just sort of this idea of this f of x, just a slightly different notation for y. Couple more just sort of recap things to recap of what I've just said. Sometimes instead of y, we might write f of x. We say this aloud, f of x, right? I've said that a lot. That should be familiar by now. And we use this notation because if I just write y, that doesn't really tell me what my input is. There's no way of knowing that x is the letter I've chosen for my input. Like if I just write, hey, I have a function y, and I circle it and I go, yay, that's my function, you have no idea what letter I'm using for my input. But if I say, hey, I have a function f of x, then you know that my function is being called f and my input is x. And so it makes it very clear what the input and the output is. And like you could see back here, when I plug in 4, I do the same thing that we were doing on this side over here. I just plug in 4 for x, and I just simplify it down. And so if here, I would read this aloud as f of 4. And when I say, hey, f of 4, that's just me evaluating this line when x is equal to 4. And so I use a slightly different thing here. If I say f of 2, that means that we're evaluating f of x, we're evaluating y, if you will, at x equals 2. And that's just sort of verbally what we would mean by f of 2. And so just to get sort of familiar with what these might look like, here are some examples of lines, and just using this different notation. So maybe instead of y is equal to 1/6 x minus 3, we're going to just use f of x here, just instead of y, and that's a good notation. We could also say, instead of like y equals 4, we could say g of x equals 4. And you notice I'm using a different letter there. I'm using letter G. That's totally fine. You can use whatever letter you want. F is definitely the most common, but maybe if you have multiple lines that you're putting on the page, you can label them with different letters: f of x, g of x, h of x, so on. And then here, lastly, this is a notation that you probably won't see very often, but just like you could write 3x plus 2y equals 1. And we've seen problems like this where I give you 3x plus 2y equals 1 or something similar, and you solve it for y. I could write this like that and then solve it for f of x. And here's something that, here's a point that I want to bring up before we move any further. You have to be very careful with this function notation. A lot of people on their first passes at functions, they think that these two things are being multiplied. And that's a very natural thing to think about, because I mean, if you think about it right here, I'm writing out f, and then I'm putting parentheses x. And you know, we do a lot of multiplication, like maybe 2 parentheses 3, and a lot of people are like, oh yeah, that's 6. Well, here in this case, this is not multiplication, and that can be tough to recognize sometimes, when things are multiplication, and when they aren't. But that's something that we'll have to get good at. We'll have to recognize when I'm using function notation and when I'm actually using multiplication. I see a lot of students try to multiply f and x together, and it really just leads them down a path that they just have they don't even really know what they're doing, because it's just not intuitive to do that. There's no reason that we actually do that. So be careful. We don't have any multiplication going on in what I've boxed right there. No multiplication there. This is just function notation. All right, so I keep using this word function. I keep saying function notation. I keep saying we use the letter F because of function and function. So what the heck do I actually even mean by that? Let's get to a definition here. This is fairly confusing, but we'll see a lot of examples to sort of make this clear. A function is a relationship. Mathematically, we say relation, but you can just colloquially say relationship between x and y. So I have two variables, x and y, and this function, this definition of a function, is any relationship between these two variables. But there's a caveat here, and the caveat is that every x that you have can correspond to at most one y value. So really what we're saying here, another way of saying this, is that you can't have one x give you two y's. And that's really what we're saying here is that if I input an x, I can't get two different y values out. That's bad. If that happens, then it's not a function. So to sort of ingrain this in our head, let's go through a lot of examples looking at a graph here. And so right here, we've got a line, good, linear function here. And the question is this a function? So let's just use that definition here. I'm actually going to copy and paste this definition. We'll just keep putting it on every slide. We're going to keep coming back to this definition here and just using it over and over and over. All right, so we got that right there. All right, so a function is a relationship between x and y in which every x corresponds to at most one y. So let's start doing this. Let's just start picking a bunch of x values. Let's pick that one. We'll keep it simple. Let's just pick all these x values that are on these tick marks. If you find the corresponding y value for each of these tick marks in red here, so all of these red are the corresponding y values for each of the blue x's, right? And that gets me to the point on the line. The question is, do any of these blue points correspond to more than one red dot? And you can very easily see that that's not the case, right? These all just go one to another here. You know, they just all correspond nice and neatly, one for one. There's no doubling up, if you will. And let's jump on to another example that actually doesn't work. And so here I'll use this sort of same thing. Let's pick some x values. I'm just going to pick these 4 right here, and let's go ahead and look. Let's look at this guy first, this second x value here. Does that x correspond to more than one y? And in this case, it does. You can see that there's 2 red dots that it corresponds with. That singular x value, that x equals 2, right? X is equal to 2 there. And so that x value is going to give us 2 different y values. So this is not a function, as a matter of fact. So yeah, so this is a great example here of something that actually doesn't work as a function. Yeah, let's keep on going here. So let's go ahead and look at this parabola right here. And so if we're looking at this, we're just going to pick a bunch of x values out. And let's go ahead and do that. So I pick my x values out and find the corresponding y values. A little bit of overlap there at the origin. That's okay. Every single one of these x values, it just corresponds to a single y value right there. And so because I don't have an x corresponding to more than one y, it doesn't correspond to 2 y's or 3 y's or 4 y's, then this is fine. This actually is a function, and it works. Yeah, so this would be a parabola here. We'll get more into that a little bit later. This guy that we've got here, this would be kind of a sideways parabola. We'll get into that a bit more later. I don't want to focus too much on exactly what these functions are for now. That'll be the next lecture, but just kind of looking at, are these functions? Let's do a handful more examples. So here we see a circle. We got a graph of a circle. We won't spend too much time really talking about what circles are in terms of functions, but for right now, let's go ahead and look at this. Let's pick an x value, and oh look, there are 2 different y values that x value corresponds to. Maybe another way to say that is that if x is equal to 1, you could be y equaling something, equaling whatever this top point is, and I can't tell exactly what that y value is, maybe 3.5-ish, something like that, 3 1/4. If x is equal to 1, you could have y equal to 3 1/4 or negative 3 1/4. either of those y values will make the function work. And so that's bad. That's exactly what we don't want, because we'll remind ourselves that every x has to correspond to at most one y. And since we correspond to two y's here, that's bad. So this would not be a function. Right here, though, this might be all right, because in this case, we actually have an x value here corresponding only to a single y value. I don't have my function down here. And because I don't have my function down there, there's really no way for me to have my singular x value correspond to multiple y's. So this would be a function that works, and we're all fine and dandy with that. Probably you can guess the next example. Instead of the top half of the circle, I'm going to do the right half of the circle. And in this case, this will not be a function for really the same reason that the circle wasn't a function. If I have an x value here, there are two different y values that satisfy this circle, that satisfy the function itself. And so this would not be a function. So one thing that I do want to say while we're here and looking at these graphically is there's a thing called the vertical line test. And what the vertical line test tells us, or really what it is it's a way to figure out if something's a function or not. And so what we do with this vertical line test is we sort of pretend that there is a vertical line. And let's go ahead, let's do this in a big bright green. So we pretend that there's a vertical line here. Let's make that straight. And what we do with this vertical line is we move it straight across. We move it straight across the graph from left all the way to right. And as we move it across the graph, what we're looking for is, does the function that I've drawn, so in this case, the right half of the circle, does that right half of the circle, this function, does it ever cross this green line twice at the same time? And you can see the moment that I hit here, boom, all of a sudden, there are two places where this function, the right half of the circle, is, excuse me, I shouldn't use the word function because it's not a function. There are two places where the right half of the circle crosses the green line. No matter where I put this green line in here. And so that means it's not a function. If I go back to here, or let's do a different example. Let's go back to this parabola here. So if I look at this parabola, we'll go ahead and make our big bright green line. And if I move this green line across, what you can tell is that there's only one intersection point between the parabola here, that curve, and the green line. There's never a place where that parabola touches the green line twice at the same time. And so that would be a great example right there of the vertical line test, if you will. It's just sort of a shorthand way of checking whether or not something is a function. Great. So we've seen a lot of these graphically. It's probably fairly easy now. You're like, okay, if they sort of overlap vertically, then that's bad. You know, we do the vertical line test. That's wonderful. But what if I don't give you something that is a graph? What if I just write out these functions like so? This is tough. There are ways to do this without actually having the graph. But they're tough, and we're not really going to get too much into them. The best thing to be able to do is to actually be able to graph these. And so for me, I've seen these before. I know what these all look like. I can do very, very quick sketches of these because I've just seen them so much that really I know what they look like. This is going to be my y equals x squared. My 1 over x is going to look something like this. And maybe I have an asymptote here. Don't worry if this isn't stuff that you're necessarily familiar with. The x plus 1 is going to look like that. And then this last guy is actually a circle. And so now at this point, you're probably like, oh, these are, okay, cool. Now I can easily say which one of these are functions. In fact, all of them are functions except for that circle. But when we're just looking at them in the context of just the equation, f of x equals x squared, f of x equals 1 over x, y equals square root of 1 plus x squared plus y squared equals 1. That's tough to do. It's tough to actually look at them and figure out, are they functions just by just looking at them. So really the way that you'll do these is you'll recognize that what these functions look like. You'll recognize, hey, x squared is a parabola and that looks like this. You'll sketch a graph of it and then you'll be on your way. Now, with all that being said, I do actually want to show this x squared plus y squared equals 1. I do want to show a little bit of algebra on how I would actually prove to you algebraically that that is not a function. So let's say you didn't know how to graph x squared plus y squared equals 1. You didn't know that that was a circle. You can actually, in this case, you can prove it algebraically pretty easily. So let's go ahead and do that. So if I start off with x squared plus y squared equals 1. What I'm going to do here is I'm going to solve for y. So I have 1 minus x squared. And now here's what I'm doing. I'm going to take a square root. But what we have to remember, this is one of the golden rules of math. Whenever I take a square root, whenever I put the square root in, I have to include a plus or a minus. And that plus or minus is exactly what tells us that this is not a function. Because if I put in a single x, let's go ahead and do this. Let's put in x equals 1/2. So here, and let's use our fancy new function notation. F of x equals plus or minus 1 minus x squared. So if I evaluate f of 1/2, that's going to be me plugging in 1/2 in for x. 1 minus 1/2 squared plus or minus, do some simplification, 1 minus 1/4 plus or minus square root of 3/4. And I know I'm doing a lot of this quickly. I don't really want to focus too much on this algebra. I just really want to focus now that, look, when I plug in 1/2, I get positive root 3 over 2 and I get negative root 3 over 2. I just got two values out when I plugged in one y value. And if we remember, that's just the exact definition of the function. That's just exactly this. Every x has to correspond to at most one y. And in this case right here, we can see that because of the plus and the minus, circled that incorrectly. Because of the plus and the minus, we have two y's that came from one x. So that's a good example of when you can do this algebraically. But for these other ones, we're kind of out of luck here because there's not really anything we can do to really convince ourselves whether that it's a function or not. All right, let's go ahead and get into how to actually do a little bit more of this algebra that I've done here and how to simplify some things. So let's consider this function here. This is in fact a function. It is a square root function. We'll get more into what that looks like graphically later and how to deal with that, but we should be comfortable with actually just evaluating square roots. So what I want to do is I want to find f of 7 and I want to find f of 1. And so let's go ahead and just do that. Let's start off with that f of 7. So I have my f of x and it's written there. So when I do f of 7, I'm just plugging in 7 in for x. So right there. Let's actually put that in a different color just to make that very, very clear. 7. Just as a little side note while we're here, if I asked you to write f of smiley face, you would do smiley face minus 3. And there's nothing else you could do there. You can't subtract 3 from smiley face. So we just leave it. That's our answer there for f of smiley face, right? So just to be very clear, it's just a replacement. Instead of an x, I'm going to put a 7. Instead of an x, I'm going to put a smiley face, and we're on our way. And so just some simplification, square root of 4 equals 9 plus 2 equals 11. Yay, we got our point. We know that 7, 11 is on this graph of the function. It satisfies it. All fine and dandy. We got f of 7. Great. Let's go ahead and do f of 1. And so if we have f of 1 here, if you're looking ahead, you might realize what's about to happen, and it's not good. I'm not going to bother writing the ones in red. We should know by now that I'm just plugging in 1 in for x. 9 plus square root of, and 1 minus 3, that's going to be negative 2. And at this point, things are bad. We don't like this. Yikes. And really, it all boils down to that square root of negative 2. We can't take the square root of a negative number. So what do we do? Well, really, we're stuck. There's really not anything that we can do at this point. Because we get that square root of a negative number, we have to really just say our answer is undefined. And I do want to be careful here. I don't want to say, so I'm going to write this out, and then I'm going to explain why I don't like it. Equals undefined, right? It's unable to be defined. You can't tell me what 9 plus root negative 2 is because you can't take the root negative 2. Here's what I don't like about this. I don't like this equals sign. That's saying that these two things are exactly the same, and that's not true. This undefined is just more of a descriptor here. And so maybe what I'd do is I would just say, I'd probably write a sentence, but I could just draw a little arrow here and I go, okay, undefined, that's our answer here. We don't, we can't actually say what our answer is. We don't actually know, undefined. And so, but this leads me to a question here. This leads me to a thought. Well, I had no trouble finding f of 7. We got 11 as our answer. That was all fine and dandy. But here on f of 1, we had trouble here. We got something that doesn't work. We got the square root of a negative number. And so I'm going to ask the question, what values of x are we even allowed to plug in specifically for this function? And really also for a general problem. If I give you any function, what x's are you even allowed to plug in? What x's are bad? Right? What x's might give you a negative under that square root? And I want to actually hone in on that right here. We are allowed to plug in x's that don't give, I'll say yield, x's that don't yield a negative square root. So any x that you plug in, as long as you don't have a negative underneath that square root, then you're going to be good. And when I look at that, I realize that I have an x minus 3 underneath that square root. So x better be bigger than 3, right? If x is anything smaller than 3, then I'm going to be taking a small number, x, and I'm going to be subtracting it by 3, which is bigger, right? And so if I have 2 minus 3, that's going to give me a negative. 1 minus 3, that's going to give me a negative. 0 minus 3, negative 1, negative 2, negative a million minus 3, that's still going to give me a negative number. And so what I'm realizing here is that x minus 3 has to be greater than or equal to 0. 0 is fine. I can take the square root of 0 and I just get 0. But that x minus 3, that part underneath the square root, it has to be bigger than or equal to 0. And so what I'd say here is that x has to be bigger than or equal to 3. That's me just adding 3 to both sides here. I can kind of squeeze that in. Plus 3, plus 3. And so x has to be greater than or equal to 3, because if it's any smaller, I'm going to get a negative underneath that square root. If you're having trouble seeing that, just try plugging in a bunch of values. Try plugging in a bunch of numbers in for x that are bigger than 3 and a bunch of numbers that are smaller than 3, and you should see fairly quickly what happens here. So this x greater than or equal to negative 3, I can say this in a slightly different way. This is what we'll call set notation. I'm not going to be super picky about you using this. You're totally fine to just write a sentence out or just write verbally, x must be bigger than or equal to 3. I'm totally fine with that. There's no problem there. If you are familiar with interval notation, you are welcome to use it. I am not going to teach it, but in interval notation, this would be 3 to infinity with a hard bracket on the 3 and a soft parentheses on the infinity. I'm not going to bother explaining what that is. If you know it, great, you can use it, and I'll totally accept that. But in this case, we are plugging in any x such that x is greater than or equal to 3. I'll say that again as I highlight these letters. X such that that bar means such that x is greater than or equal to 3. And there we go. Those are the x's that we're allowed to plug in here. And so that's great. That's wonderful. We've got this idea of what x's am I allowed to plug in. Keep that in the back of your head while we're thinking about what x's we're allowed to plug in. Let's sort of shift gears and think about, well, what outputs could I even get? What y value? What could I get given that I'm only allowed to plug in these x's that I've circled in purple here and written in the red in interval notation? What y values are even possible to get out? Would it be possible to get -4 for y? Could you find an x that gives you -4? And when I look at this, I don't think that you can. And there's a reason here. When I look at this square root, just this boxed square root part, I'm going to take the square root of something underneath it, and that something is going to be positive or it's going to be 0, right? We just said that before. X minus 3 has to be positive. We saw that right back here, right? We said, hey, x minus 3 has to be greater than 0. And so what's underneath this square root is going to be 0 or bigger. And then I'm taking a square root of it. And I can guarantee you that you've never taken the square root of a number and gotten something negative. This right here, I'll write this out, square root of yada, yada, yada equals negative different yada, yada. That has never happened before. This is bad. It just, it doesn't work. You cannot get a negative number when you square root something. And so what I'm recognizing here is that this term cannot be negative. And so right off the bat, I recognize that I'm adding 9 to it. So my answer is going to be at least 9. There is no way for me to get an output any smaller than 9 because this term can't be negative and this is always 9. And so that's this idea of, hey, what values of my output, what values of y, what values of f of x are even possible to get out? And the smallest that this boxed in the red can be is 0. So that makes me say that the smallest value of f of x that I could get is 9 because I'm then adding 9 to it. And so what we would say in this sort of set notation, I'll verbally say that again as I highlight, all the possible y values that I can get are any y such that y is greater than or equal to 9. And let's do that one more time. The y's that I'm allowed to get are y such that y is greater than or equal to 9. And that's all fine and dandy. So we know here, looking at this, we had to do a little bit of thought process on this square root and convince ourselves that the smallest that could be is 0. But that right there, it just immediately tells me what my smallest y value I could get as an output. It's not possible to get -4. It's not even possible to get 8. It's not even possible to get 8.9999. The smallest that you could get is 9. And let's do interval notation just for those that are familiar with it. 9 with a hard bracket up to infinity with a soft parentheses there. That would be my interval notation there, if you're familiar with that. So we've talked about two things, and I'll come back through just to remind ourselves of exactly what those were. We asked ourselves what values of x are we allowed to plug in, and we also asked what values of f of x, what values of y, what values of the output are even possible to get. And so those two questions lead us to two definitions, domain and range. And I'll try not to just read off exactly what we've got here. I'll try and verbalize it in a way that'll make sense to what we've been talking about. Domain is just every x that you're allowed to plug in. Range is every y that you can get out, right? And so on this example that we've been dealing with, the domain would be that x greater than or equal to 3. If I wanted to be specific, I could say x such that x is greater than 3. Again, I'm not going to be too picky on that here. The range is going to be that y such that y is greater than or equal to 9. And there we go. We've got our domain and range for that specific example that we looked at. And that's really all it is. We've spent all this time talking about these things. What x's can I get out? Well, that's just this, we have a word for it. We call it domain. And we spent all this time talking about what y's are even possible to get out. And well, we have a name for it. It's range. And so that's the domain and range of a function there. So one last thing that I want to say before I let you go is that with this idea of domain, you can overthink this concept a lot. Really, for our purposes, we're going to encounter two main things that cause our domain to not just be everything. Most of the time, the domain of your function is everything. You're allowed to plug in any x that you want. But we saw one example here with the square root where it sort of restricts us from plugging in anything that we want. Like on this example, we weren't allowed to plug in anything smaller than 3. And so these two things here that make it so that we don't just have our answer be all values of x. The two things are having a negative under a square root, as we just saw, right? If you have a square root in your function, you can't take a negative. You can't have a negative underneath it. That might restrict what x's you're allowed to plug in. And the other thing is dividing by 0. So if you have a fraction and you have an x or anything on the denominator, I don't know, maybe you even have 1 over x minus 2, right? That denominator can't be 0. Dividing by 0 is not allowed. And so for our sake, these two things are going to be the main two things that cause our domain to not just be everything. There are a lot of other reasons. There are other functions out there that have, their own issues, if you will, but we're not really going to get into a whole lot of those. These are the two main ones that we'll be talking about. So domain and range, if I give you a function, I say, hey, find the domain and range, your thought there is, for domain, am I dividing by 0? Do I have a negative in my square or under my square root? And for range, you have to think a little cleverly. You have to think, okay, what y values it is even possible for me to get out? Can I have, can this term be negative? Can this term be bigger than 3, et cetera, and all those sorts of thoughts that'll go through your head. We'll get a lot of practice on all that with the worksheet. But for the lecture here, I'll go ahead and call that. And that'll be the day.